Hi, now that you have learnt about the fundamental control tools, especially transfer functions, you can now analyze the behavior of open loop systems with time and with step inputs. In the last class, you also learnt about the robot joint. So now you are ready to create closed loop systems for precise positioning and velocity control of the joints. Okay, so in today's class, we'll discuss feedback control, commonly known as PID controller, or together PID controller, that are most widely used kind of controller for industrial robot systems. So yes, in general, closed loop system of typical industrial robot looks like this. So what all in blocks, what all things you should see normally if you just look around the controller of your industrial robot. So this is what you desire that comes from here. What you desire is normally you can feed your robot's joints with its joint velocity and joint position. So that goes here, and that is in a set of 6 if it is a 6 degree of freedom robot. So it comes as a vector form of all the 6. Okay, so that goes here. So it goes here with as an input. Okay, and let us say if you take from here, so this is your actuator that goes into the joints of your robot. So output of this is connected to your manipulator. Manipulator is basically your robot arm that takes in different kinds of disturbance due to payload, due to its supplementary load, due to the environmental disturbances, okay, wires and etc. So those disturbance will come here. Finally, whatever torque you put over here through the current that you are putting, okay, so that goes as an output to the end effector. And at the joints you also have sensors. Okay, those sensors gives you the actual feedback of the joint position and joint velocity. So that goes through the feedback elements. These are nothing but transducers which converts it to equivalent form how we desire it, so that we can compare them. Two signals of the same form needs to be there so as to be compared. Okay, so if it is optical encoder, you may have optical encoder to some kind of signal converter, so that it goes to your digital system, a PC based system, or maybe a typical embedded system. So that comes here. Okay, so now after comparing what you have desired and what is actual, so you get an error signal. So that is what is a tracking error. That is, if it is a velocity control or if it is a position control, it is just a state error from the desired one to the actual one, and that error goes to the controller. Controller can be your PID controller or various other kinds of controllers which are there. Okay, so that controller now gives a signal to the power amplifier. Power amplifier basically converts the incoming signal to the actuator compatible power. Okay, so if it is 0 to 5 volt signal, so it can be if it is 24 volt motor which is there at your joints, or if it is a synchronous motor, it can be AC signal also. So accordingly this power amplifier will convert the type of load, electrical load, that goes from here to here, that is acceptable to the actuators. Finally actuator drives your rotor. So this completes your complete cycle. This is known as a feedback control cycle. So this basically is a closed loop control system. We'll look into the detail of each one of them. So what goes into them, okay, what is here, what is here, what is here. So we'll see that now. So while I was discussing actuator, you saw few kinds of drivers. Those were nothing but the power amplifiers. Okay, that took input from my controller. So that was the signal that goes to the power amplifier. So at least this portion, this two portion was covered already in your module, which was actuator module, that was module 2. And sensors, a lot of sensors you have seen. So there are nothing but joint angle sensors. It can be optical sensor, it can be Hall effect sensor, magnetic one, or it can be potentiometer. So any kind of sensor can go here. So This and this is already covered. So now we'll talk mostly about controller, feedback systems and comparator, and overall whole of this system will be clubbed together as an robot. Okay, so this will be one single system known as robot. Okay, so let us continue now. So yes, again starting with second order linear system, you know your robot controller can also behave in a similar manner. Only thing, the constants may differ, rest things are very much analogous to this. Okay, so Ft, you know, it is the input force to obtain the desired displacement. What we need now is a critically damped system for faster transient response. If I have commanded to go to a particular place, let's say this one, so joint, if it starts from 0, it immediately should go like this, and it should almost reach to the desired commanded position. Okay, so this is your commanded position or the desired position. This is the actual rotor angle that I want. Okay, so this is your rotor angle with time. So a kind of behavior I should get, and I want this to be critically damped. Why? I want a fastest response, fastest transient response. Okay, for position is xt of the block at any instant of time. For this, xt is there, that is to indicate the displacement at any instant of time t. xd, xd dash and xd double dash are desired position, velocity and acceleration. Okay, now let us start some introduction to control over here. Okay, so basically we'll be talking about feedback control using damped spring mass damper system that is here. Okay, so let us just assume this is not a controller which is fully built now. Okay, so this is your system, which is your second order system. Okay, you are already familiar with this. Output is now sensed, position and the velocity. That is coming here as a feedback. So here goes your velocity feedback, here goes your position feedback. This is the desired position, this is the desired velocity. This is the summing block 1, summing block 2. So one of them is calculating the error of velocity, error in velocity, which is coming from here and which is desired here. Basically that is compared here, this minus this, and calculated the error in velocity. Okay, similarly this one is for calculating the error in position, and both of them are fed to the constants which are there. You already know, if it is a block, a signal gets in and a signal goes out. So output signal by input signal is the transfer function which is here. It can be simply a gain. Okay, a gain is nothing but a constant multiplier which is here. Okay, so this is Kp. Kp is position gain and Kv is velocity gain. So putting them together, it goes here, and this is the desired reference acceleration that is coming here. Finally that goes here as a force. So there may be something in between which converts all these position errors, okay, and to equivalent amount of force that is required to do this kind of control. So this force gets into the system that finally drives your second order system, which is spring mass damper system, and output you are getting as position and velocity. Okay, so this is a closed loop which I am going to frame here. Okay, so the control input over here may be indicated as F is equal to Kp times of, Kp is this one, Kp is this, xd minus x, xd is desired minus actual, that is the error, Kp into error in position, Kv into, similarly you can write error in velocity. So equivalent force that is generated due to the errors is F. Okay, so that effectively goes to your system. So let us now move ahead and see. So in order to do position control of the block regardless of any disturbance, let us say there are some disturbance, I want to reject them all and I still want to go to my desired condition. Okay, so let us say I have started from rest and I want to maintain my position at that zero input. Okay, zero input for position as well as velocity. Okay, so this time I'll equate them to 0 now. So it was xd minus x into kp gain. So if you are desiring this to remain at 0 0 position, so this becomes 0. So effectively what you see here is kp into x, negative comes from here. Similarly for this one also, because it is the force which actually drives your second order system, so your force balance equation for that second order system is this. You already know this. M is the mass, B is the damping, K is stiffness. So this is what you should get. Okay. Okay, so this can now be written as mx double dot b plus kv. I'll take down everything to left hand side of the equation and I'll get this one. Okay, now I can write again b plus kv, that is the damping gain. Okay, that comes here as b dash. Similarly kp plus k is k dash. Okay, so this is your new system where b dash is b plus kv, k dash is k plus kp. Okay, so by suitably adjusting the feedback gains, these are known as feedback gains kp and kv, this second order system, this one, may be critically damped for fastest transient response. Naturally it may not be fastest transient response. The system characteristics says that it is not a fastest response. It is not critically damped for any step input, let us say. Okay, so it may be oscillatory in nature by its own characteristics, that is by taking m, b and k, it is coming out to be oscillating behavior. It can be a over damped system, it can be under damped system, it can be anything. So what I want is critically damped system. Now I can use this feedback gains to adjust the characteristics equation, that is b and k equivalent values given by b dash and k dash, to a response such that you get to this, that is the discriminant of this characteristics equation becomes equal to 0. So in that case your roots will go equal and it becomes critically damped. So that is the case here. B dash square is equal to 4m k dash. This is the case you wanted. So b dash square minus 4m k is equal to 0. So this is the discriminant going equal to 0 for this characteristics equation. Okay, so now you see, using such kind of feedback, so you can bring your system to a critically damped system. Although your system was not critically damped naturally, but you can make it critically damped. Okay, so yes, this time your system equation can be written as f is equal to kp xd minus x, kv xd dash xd dot minus x dot. So it becomes equal to kp into error in position, kv into error in velocity. E is the error in desired and actual position, E dash is error in the desired and actual velocity. Got it? So yes, now you can write your system like this, because you know you have initial zero condition for position and velocity. It comes out to be like this, f is like this. Got it? Okay. Taking Laplace on both the sides of it, what do you get? Fs is equal to kp es, kv s into es. Okay, so that comes here. So if you take common es from this side, so what do you get? Fs is equal to kp s kv into es. So basically Fs by es is equal to kp plus skv. So this becomes the transfer function. If I represent that as a block, so my block has got a controller which is given by kp plus skv. Input is my error gets into this, so that goes here, and finally you get output as force. So output Input is the error, output is force signal, and this is your transfer function for the controller. This from now and on we'll call it as a controller. So this is what is your controller. We'll get into more details of this. We'll make this controller even more advanced now. Okay, so this is your controller that takes in the input. Okay, how was your system? Your system was very much like this. So it was force that got into your system. So this is your system, gain for which is given by Gs is equal to 1 by ms square plus bs plus k. You know that already. So input was force to that, output is displacement that you can measure. Okay, so this is your system. You had already controller that is given like this. So can we put everything in place now and represent the system as this? You see what it is now? So this is your system that takes force as input, gives you access, that is the displacement, as output. You are taking a feedback that goes in this line, finally it gets into here, and xd is the desired input displacement that you want actually. So the error which is here from the desired and the actual one is the error. So you take difference of this and this, and this is your output after taking the difference. So this is known as a summing block basically. Okay, so error is calculated, error gets into the controller and it gives you force as an output. So that is what you already have seen here. So this is the, your controller takes in error, gives you force as an output. Okay, so you can represent your system very much like this. Okay, so this is very, very clear. Okay, now can I have a equivalent transfer function for whole of my system, including the controller and the actual system which is there? So controller and the system are in series. Okay, so they can be, we can take product of them. So taking product of that will become GS into KP plus KVS. So that is what is shown here. Okay, so both of them goes together. Okay, that comes here. So whatever is the output, XS and XD. So XS minus XD gives you the error. Error multiplied by the product of this should give you the product of here to here should give you XS. So now I can write it in compact manner like this. So whatever is the output, output is error that comes here, that is x desired minus actual, that is the error. Okay, and equivalent gain which is there, so that is from here to here, so that goes here. Okay, so this equation is fine. Now what I'll do, I have just put down this here once again. Okay, same equation. Now I can rearrange this and write it in this form. I have just taken XS by XD form now. Okay, taking common from XD from this and taking XS also to the left side of the equation, and I can express it like this. So what you have seen here, this is very much like our old control closed loop controller that I have discussed earlier in transfer function. So if this is GS, this is the output, closed loop comes like this. So this is your HS that was also there earlier. So this is your input. So closed loop transfer function for whole of this is GS by 1 plus GS HS. This time you see you have unity feedback. That means there is no gain over here. You don't have any HS. HS is equal to 1. So in that case, GS by 1 plus GS. And what is GS? GS is product of controller and your system. So it is supported by that also. So this is exactly same way you can derive this also. So this is what is your equivalent system transfer function that represents the output, that is the actual displacement, and the desired input, that is commanded input, as XD. Okay, so this is here. Okay, now the characteristics equation for this should be the denominator, equating the denominator and finding it the roots of that finding the poles for that. So that goes like 1 plus gs kp plus kvs. Okay, and what is that? Gs is 1 by ms square plus bs plus k. So I have just put it like this over here and I got to this. Okay, I got this as my characteristics equation. So I have obtained it earlier also. So it is ms square plus b dash s plus k dash. Okay, whereas b dash is kv plus b and k dash is kp plus k. So it is exactly the same thing. Okay, the system can now be critically damped when the poles are equal. You know that through your earlier knowledge, we have discussed in earlier lectures. So that in that case, this is a second order system. So it is having two roots, s1 is equal to s2, and that is the case when b dash is equal to 2 root mk dash. 2 root mk dash. Okay, so that is there. So you can put those values here. So yes, in this case, the position control gain Kp is known as proportional gain, stiffness gain. Both are same. Okay, it is known as proportional or stiffness gain, commonly denoted as P gain. Okay. Next is the velocity control gain Kv. Kv here is also commonly known as derivative or damping gain or D gain. Okay, so these are the common terminologies which are used in context to any industrial systems. Okay, even in control. So yes, now what you have seen here, proportional and derivative gains, they don't meet all the control demands. Okay, you can make it critically damped. So yes, if this is the desired output you want, okay, so your system can just go like this. It just starts from 0, it goes very much near to that, and it is critically damped. But it has never reached to the actual value. You see there is some difference. So this is a common kind of critical damping behavior that you will see in your system. We have seen it earlier through plots also. So what is this basically? This is this gap is commonly known as steady state error. Steady state. So it has already become almost steady. Okay. So why this is happening actually? So basically proportional gain, that is the stiffness gain, if you increase that, it makes your system very much like a spring. So you have made your spring dominated. Okay, so you have increased the Kp value basically. So it will behave more like a spring. So it should make it like a oscillatory in nature. Okay, what happens when you put damping? You put damping, it will reduce the thing, but now again it will reduce the damping. It can make things very much critical, but it will also lower this line. Okay, so that increases this. So finally you end up in this. Okay, so effectively it creates a force based on the error. Okay, so that is Kp and E dot into Kv. So what you found, there may be a error which is negligibly small for the velocity as well as for the position. So you don't get enough of a force so as to exactly get to the actual demanded value. So as your error gets reduced, so there may be a time when you don't have enough of force to drive your system also. Okay, in that case it can get stuck, or by natural way, even if there is no friction, it has natural situation when it lies somewhere over here. It can bring your system only to this. Okay, so that is your steady state error. So you see your proportional and derivative do not meet all the control demands. Okay, so a new kind of gain that is introduced is known as a integral gain. For position control, we'll see here, we are talking about position controller first. Okay, so if it is a position controller, so adding integral gain in the control law eliminates the steady state error for step input. Okay, step input here. Okay, so I have just demanded for a step distance for this block to go. Okay, and I'll just see how my system is behaving. Okay, so this is this now my new equation will be, it is it is x d minus x kp and plus kv x d dot minus x dot. Now there is yet another term which says ki, this is integral gain, this is integral of the error, so it is x d minus x into dt. Okay, so this term may be defined as, it is a error integrated over a period of time. So if the system sees a behavior which is like this, so you have desired to take it to this, but your system follows pattern like this. So if it sees the same gap over a period of time, okay, over a period of time, it keeps on adding that error over that period and multiplies that with ki. So it will further take it to your desired input. If again it has seen error over a period of time, again it will take it to the desired signal. Finally, it reaches to the actual value. So this is what this is intended for. This term integrates the error over a period of time and does the final correction. So this can make your system critically damped and take very near to it, but that steady state error that remains, so that can be removed by this gain, that is integral gain. So this time my system equation can be written as, this is your system equation, okay, dynamic equation of motion for your system with the force input. So how much is the correcting force? It is kp into x. I assume I am tending to go to 0 values, 0, 0 dot and 0 double dot. So that is the 0 position, velocity and acceleration. So that is what I want. So I want my system to be there. I want to do step input and I see how my system will behave. So this time that is for 0 input. So this and this can be put to 0. So my system equation becomes very much like this. Okay. Now the controller. Okay, controller transfer function would be XS, ES, GS. This time you don't just have this and this, you also have this term. So what is this? If you take Laplace of this, what you get basically is Laplace of an integral should be 1 by S XS. So K times Ki is multiplied over there, so it becomes, the term becomes like this. So you have taken XS common, brought that to the left half and you got Ki by S. So that is visible over here. So taking Laplace of this gives me this. So XS and ES, so that relates the displacement XS for the ES that is coming here as an input. So this is the product of GS and the controller gain, GS and the controller gain. Okay, so that is controller is Kp plus Kvs plus integral part of it, that is 1 by S Ki. So that is here. GS is the system gain, so that is GS. So error is converted to the output like this. Okay. So this and this is related. Now if I put them all together and relate them again, so output by input should be XS by XD. So it is, in the numerator you should see the product of this and this. So GS into this by 1 plus same value that goes here. There is no feedback transfer function over here. So that is equal to 1. That is a unity feedback which you have seen. Okay. So this is your overall transfer function for whole of this system. Okay. This term, the term Ki, is known as integral control gain, denoted as I gain. Okay. Okay, so now you are familiar with P, I and D. PID. So overall, let me just summarize them all, what things that you have seen. So this is desired, that is the reference input. This is the output. You have a feedback that is given from here. Taking the difference, you calculated the error. And three blocks were there, P, I and D. Each had the terms which were inside as, first one is Kp that comes here multiplied with the error. This is stiffness gain, okay, stiffness transfer function. Next I will come here, this is what? Kd into rate of change of error, and multiplying with Kd you get the signal. So based on the same error goes to all the blocks, P, I and D blocks. Okay, each one of them creates a correcting signal based on the error. Okay, now coming to integral gain now. So how much is that? It is Ki into error integrated over a period of time. Okay, that comes here. And finally they are summed together and you get to see the total output over here. Okay, and that goes to your robot arm joints and you see the actual angle. So this is how it works. Whole of the system, which is PID system, is working. Okay, so P is the correcting signal proportional to the error. I is the correcting signal is proportional to the error integrated over a time period. D is the correcting signal proportional to the rate of change of error. Okay. Okay. Now, what are the applications of this? In general, PD is applied for any faster system. In that case, if it is very dynamic in nature, okay, you don't get the time to integrate over a period of time, your system is very, very fast. So, in that case, you can have a system which is PD control. So, that is for motor speed with fluctuating load. If the load is fluctuating, motor speed gets fluctuated. Let's say you have a generator with varying load on it. You are having a 500 watt generator for your domestic purpose. You have switched on a heater all on a sudden. What will happen? It will have some back torque, okay, a torque that comes due to the load all on a sudden, okay. So that will try to slower your speed, but you want to maintain your speed in order to maintain your frequency. So changing the speed changes the frequency. It should be 50 hertz. So in general, your alternator normally rotates at a constant speed because you want to maintain the constant frequency. Okay, so that is just one example. Even this is true for even any let's say if it is a locomotive train also, if it is loaded, if it is unloaded, so same engine can drive it at different speed. If I want to make it go at a constant speed, I need what is a dynamic controller. That a PD controller is quite good enough for this. So PI is most suited for slower system where you get enough time to integrate over period of time. If it is very, very slow, taking derivative gain for taking rate of change of error is also slow. So this becomes not much effective. In that case, PI is very much suited for slower system, like tilt control of a moving solar panel along with the sun. Okay, if your sun is moving, your panels are moving, so as to get the maximum efficiency of your solar panels. Let's say you have a system like that, so it takes whole day to take it from one position to the next position. Okay, that is sunrise and sunset. So you have a whole amount of time. In that case, taking derivatives is not much advisable, so PI is quite good enough. In either case, P is very much accepted. Okay, so this is just PID control. As a summary I have shown you. Now let us apply them for our system. So let us say I have a system which is M, B and K like this, 1, 1 and 1, and I want only position controller to be there. I want to maybe at rest with KV is equal to 0 I want to see with only proportional gain. Okay, so my system gain is like this, 1 by s square plus s plus 1. So now the poles are complex conjugates, you know that results in a damped oscillatory behavior. This is not at all acceptable in robotics, you know that. Your robot should not oscillate once it picks any load or it is going to pick a load. Okay, so for kV is equal to 0, the closed loop transfer function would be, so if you just take your system which was just calculated now, so you see xs by xd is equal to kp by s square plus s by 1 plus kp. 1 plus kp, you have kv is equal to 0. Okay, so this can now be written as, so I'll just show you the slide which was there that actually related both of them, xs by sd in case of this type of system. If you don't have any ki, you don't have any kv, so it is only kp which is here. Okay, in that case your system transfer function would be xs by xd, so in that case it becomes kp only. Kv is equal to 0, ki is equal to 0, so numerator will see only kp. So in our case it is 1, so only 1 will go there. Okay, and in the denominator also you should see 1 plus gs, that is s square plus s plus 1, and you have only kp which is here. So now I can write my system very much like this. If I put the damping coefficient and natural frequency omega n form, you have seen it earlier. So if you can convert this to this form, the coefficients of the characteristics equation will be 1, 1 and 1 plus kp. Okay, this time comparing the coefficients, I can just see 1 goes here, 1 goes here, and 1 plus kp comes here. So if I compare them all, so what I'll get, omega n square is equal to 1 plus kp, and the second term, that is 2 xi omega n is equal to 2 xi root over 1 plus kp. In our case this is equal to 1, so xi becomes equal to 1 by 2 root over 1 plus kp. Okay, so now I can do this quickly. So if it is to be critically damped, let us say just analyze the critically damped condition, you know gains can only be positive. So if I take 1 over here, what it should give me is, if I square both the sides, it should take you to 1 by 4. So kp is whatever value I want, should be 1 plus kp. So kp can be calculated like this. If I just calculate it, I see kp comes out to be negative. So I see it is not possible to take it to critically damped condition with just proportional gain. Okay, so I'll do something else. So let me just take some values. Conveniently I have taken it as 15 over here so that I can take the root of this. So if it is 15, so it square root of 1 plus 15, it is 16 root, so it is 4. Okay, so 4 comes here, 4 to the 8, so damping coefficient comes out to be 1 by 8, so it is 0.125. Okay, again another value, again for the same reason I have taken it as 16 by 9. In that case I get damping coefficient as 3 by 10. This is little higher value. Let me just see how does it behave now. So in order to do so, I have used this MATLAB code once again. So this is a common code. You can just take one of them, change the parameters which are here, and run the same code with different values of kp, kv and all. Okay, so yes, so this is your numerator. System is transfer function of numerator and denominator. Denominator is here, numerator is here. So that is your system transfer function. kp is 15, numerator 2, kp is 15, denominator is this. This is your this is the system I want to create for my transfer function, that is the controller. Okay, so that is 1, 1 and 1 plus kp that comes here. This is your transfer function for system 2. Okay, so yes, this time it is, this is your natural system. that will be plotted. This is the system with the controller. Okay, so numerator 3 and denominator 3 will be kp. So this is new kp value that is here, that goes here, and this is the third system. This is with no controller. This is with kp is equal to 15. This is with kp is equal to 16 by 9. So system 3 is the transfer function defined by numerator 3 and denominator 3. Step input, I am doing that analysis. I am just labeling the Cartesian axes grid on, so I can see the plot which is very much like this. So with no controller, this is the system, okay, the blue one, okay, and with kp is equal to 15, so it is the red one. So you see kp is higher in this case, kp is very high, it is 15. So you see, because you have increased the stiffness gain, your system becomes very much oscillatory in nature. It goes very much like this, okay, although it dampens out very near to the actual desired value, that is the step input. So it comes very near to this, but that is the steady state error which is there. System is oscillatory, it came more nearer to the actual desired signal. So this is the steady state error which is there. Now look at the 16 by 9. You have less stiffness. Okay, in this case also your system is oscillatory and it is settling at a distance which is larger than this. So you see you have more steady state error in this case. So steady state error is little higher in this case. Okay, so what do you observe here? So as kp increases, steady state error reduces. So increasing the kp gain reduces the steady state error. Okay, and for low values of kp, steady state error is high with reduced oscillation. So basically kp increases the oscillatory nature. Okay, so it makes your system very much oscillatory, but it takes you to very near to the desired commanded value. Okay, but again steady state error is there, but it is less. Okay, so the remedy is to reduce the oscillation for the reduced steady state error also. Okay, so you have to reduce the oscillation as well as steady state error. Okay, so this can be done by introducing the velocity, that is the derivative controller. So we'll see again by the same example. Now I am introducing kV also. Okay, so this time same system. I know it is by naturally it is oscillatory in nature. Okay, so position and velocity controller, it is PD controller I am going to do. So my system gain is now given as this. You have seen it by analysis that we did earlier. So whole of my system output by input, that is the desired KD XD value and the actual value XS. So ratio of that is giving me this system transfer function. Okay, so this time m is equal to 1, b is equal to 1, k is equal to 1 gave me this. Okay, so I have just substituted m, b and k values and I got to this. Again comparing it to the equation which is given like this. Okay, this time the second term to second term, third term to third term can be compared once again. So I should see omega square is equal to 1 plus kp. Okay, omega n is equal to square root of 1 plus kp, and 2 xi omega n, that is the second term, comes here. So this implies 2 xi instead of omega n, I have just put it here. So this is the relation between kp and kv. So this is what I can use for any value of kp. I can get the value of kv also. Okay, so let us start. So velocity gain is to be introduced to reduce the oscillation. Let us take, we had a better one for that reason, that is kp is equal to 15. We saw, so this was the case that we want to do enhance upon. Okay, so let me just show you first, show the plots first. So this was kp is equal to 15, that is the red one. So this is the oscillation. It took you very near to the commanded value. I just want to reduce the steady state error also, and I want to reduce the oscillations first, but I want to have a better near value to the commanded position. So having this value xi is equal to 0.6, if I put it here, okay, and kp is equal to 15, that is from here I got kv is equal to 3.8. This is just a trial value I want to test. Okay, again for critically damped condition, you should see xi is equal to 1. Kp, I want to work upon the same one. This time I got kv is equal to 7. Using this equation I could get it, or directly from here, this is same, both are equivalent. Okay, so yes, for xi is equal to 1, that is for critically damped condition, that is what I desire. Kp is 15 and kv I got it from here, I have worked on this. So this is the critically damped condition. Okay, so let me again see using a similar code. You can see I have created the systems over here for kp and kv value, which is here. This is my original system without any p or d controller. This is the second system with kp and kv value this. This is the third system with kp and kv value this. Okay, and your without damping, only stiffness. So kp value is 15. So I can create my fourth system and took step input for all of them. So I got a system, all the systems in one place now in order to compare it better. Okay, so this is the first one. This is the top one, which is here, that is kp is equal to 0, kv is equal to 0. This is my original system. Okay, the second one is here, that is kp is equal to 15, kv is equal to 3.8. So that is my red one that comes here. Okay, so you see it has overshooted quite high, and it got little bit of oscillatory nature also. So that is what is not desired. So now I'll look at the system which is here. Kp is equal to 15, kv is equal to 7. Okay, so that is the system which is here. Okay, that is the yellow one. So you see it has also overshooted a bit, but it took you very near to the value with similar steady state error. So less overshoot you are seeing here. Okay, and but there are steady state error in all the cases. This was the system with kv is equal to 0. Okay, so that is only stiffness with its own natural damping. So this is with only external stiffness, that added stiffness that is done. So you saw it is oscillatory. I don't want to talk about that now. So three systems are here. Best one can be this one, which is just overshooted a bit. Steady state error is there. Okay, now can I work on this? So this time for step response, steady state error is observed. Okay, with settling time as 0.938, it has almost settled. For critically damped systems, so just oscillations getting minimized. Oscillation is now minimized. This now requires an integral gain to be introduced. So you saw there is a steady state error. That can now be eliminated with the best value I got, so that I don't see any steady state error. So can I do it now once again? So let us start working on that. So the substituting gs is this to this. This is the transfer function that we obtained for the PID system. Okay, just now. So xs by xd, that is the system transfer function with PID controller with kp, kv and ki in place. This is my system transfer function that is here. So if I put them all together, I will get to this. So this time it is not a second order system, you see. So kp and kv you have already put there. Okay, and you saw the best behavior. I'll just do a trial with one value of ki. So You with your system m is equal to 1, b is equal to 1, k is equal to 1, substituting it here, I got this. So this is my system. This time I have used ki is equal to 2. For critically damped system, kp and kv, this that has done a best job earlier. So it eliminates the steady state error to 0. How? I'll show you. Same, I have done exactly similar stuff here. I have 4 systems defined with different gains like this, with my original system also defined over here. So this time the behavior is very much like this. So the critically damped one is PD1, only stiffness gave me oscillations. No controller is this one, with PD is only P is this, with PD is the yellow one which has steady state error only. Okay, but we were happy with this, so we put I to this only. Okay, so this time you see, so with little bit of overshoot, with almost no oscillations, and it reached to the desired commanded value. Okay, so now you saw it was very much difficult selecting the gain. You understood the problem where it is. Okay, you saw the state of your system, you improved upon your p value and gain I value, d value, all the gains you have adjusted. But you see, it is very much based on your experience, your trials. So this is one of the biggest challenge even now when you have to select the gains, at least for even for a single system with single input and single output system. So forget about the multiple input, multiple output, coupled system, higher order systems. So it is really very difficult. So there are various approaches to this. Few of them are heuristic in nature, when you just do by trials experimentally, and it is proven it works well, at least in industrial systems, where you have very good amount of gear reduction in your robot, they work very well. Okay, so the gain selection for PID controller, that work is known as a tuning of gains. So you tune your gains now. So common design thumb rule is to set Ki is equal to 0. Start with no integral gain. Just adjust Kp and Kv to obtain transient behavior. Okay, so transient behavior includes the rise time. So that is better if you increase Kp. Settling time. So if Kj is an effective stiffness for a flexible joint is not a stiff joint. You know, it has damping, it has a natural stiffness also. So they are resonant also, resonant at Kj by I. It is given by resonant frequency, which is Kj by I. Kj is joint stiffness, I is the inertia. Okay, so that is what is here. So resonant frequency is omega j given by Kj by I. So limit omega n such that Kp by I, by setting the Kp value such that omega j is less than half of omega j to avoid excitation of joint resonance. So you have to adjust the Kp value such that you should not get to a system which is resonant with the system frequency also. Okay, this is this one, resonant frequency of your system. So you should not make it oscillate so that you get to a very high value of resonant system. Okay, so you should avoid that. So in order to do that, you have to take omega n, that is given by square root of Kp by I. Okay, this is as a thumb rule you should do. And note, Kp will reduce the rise time. Higher is the value of Kp, it better reaches to your desired position in the fastest amount of time, and that improves your rise time and steady state error also, but it will never eliminate it. It will keep on oscillating like that. With natural damping, it can see little bit of damping behavior also. But yes, Kp can never take you to that. So now what you should do, you introduce a derivative gain. It is not always true that Kp is not going to take you to a very good system. If your system is naturally damped to a very high value, so even just having a Kp is quite good enough. Okay, but you rarely see such system. Okay, so the derivative gain kV will have the effect of increasing stability of your system, that is reducing the overshoot. So having a kV value will reduce the overshoot. You have seen it by earlier example also, and it improves the transient response also. Transient response. Okay, Ki will eliminate the steady state error, but it will make the transient response worse. Okay, so be very careful. So overall thumb rule is, once Kp and Kv are chosen, so Roth-Hurwitz criterion can be taken, that is given by Ki is less than or equal to, B is there already, Kv you have chosen it, Kp is chosen, I is already there. Okay, so using the system constant, that is B and I, putting your gains that you have chosen, you can calculate the value of Ki. Okay, so this is the characteristics table, how Kp, Kv and Ki is going to affect your system. So Kp decreases the rise time, increases the overshoot, settling time, small change you will see, steady state error will decrease. For Kv, rise time there is hardly any change, overshoot will decrease. If you improve upon Kv, overshoot will decrease, settling time will decrease, steady state error, small change will be there. Ki basically decreases the rise time, increases the overshoot. This is what is told here also. Ki can make your system even worse. Okay, settling time increases. So again this is a problem. Steady state error, it will eliminate. Okay, so Ki is just a tool to eliminate the steady state error. Okay. Okay, so that's all for today. So you have seen how to control your robot joint earlier. Today you have seen the kind of controller you can have at the joint and use your feedback to take it to a commanded position in a better way. So this is not all. There are many things to learn in control. So this is just an introduction to control that we did in this module. So you have plenty good amount of reading which is remaining. So I have just noted here chapter 10 of Introduction to Robotics by S.K. Saha, that is the book, textbook by McGraw-Hill. Okay, that you can go further. This is a suggested reading. There are many control books also that you can follow. So yes, in industrial system, this hardly you can do much of a controller part of it. But yes, if at all you are given a system parameters to control, so definitely you can do it, make it much better for your application. So yes, with that we'll end today. That's all. Thanks a lot.